Hi, let's look at our modules tutorial 4 solutions. Okay, the first question is uh, getting us to think back about the interrupt service routine approach. Okay, as we know, in a application, you will have your main routine that is running, correct? And at any point of time while it's running, if a device is configured for interrupts, okay, so if I generate a interrupt at this point, what will happen is I'll be able to jump to what we call the interrupt service routine, do something, and I will come back when I return from the interrupt service routine, and I'll come back to where I left off and then carry on from there. Okay, the important thing about interrupt service routines that we do not know when they will happen, correct? It's not like a normal function call. Okay, they are basically configured to capture certain events as and when they happen, and when they do, you'll automatically stop whatever you're doing and jump over to the interrupt service routine. Okay, so for this first question, we are given this flow chart, okay, and we are asked to explain some of the potential issues with this design. Okay, so let's look at what is happening here. So first, at this ISR, I will take in the input data, process the data, and after I process it, I have a loop over here. Okay, so this loop is basically to check whether the output device is ready, and once the output device is ready, I will be able to send the data out, and then I return. Okay, uh, so what is the issue with this design? The issue with this design is actually this section over here. Okay, why? Because as you can see, I am in a loop waiting for the output device to be ready. Okay, and what if, okay, for some reason, maybe the output device is in some error state or something else happened and the output device is never ready, correct? Then I would potentially be stuck in this ISR forever. Okay, so if you look back at the concept of ISR, if I am running my ISR and suddenly at some point of time I'm stuck there, I will never be able to return back to my main routine, and I'll never be able to carry on with the rest of the activities that I'm supposed to do. Okay, because I'm stuck in the ISR. Okay, so you should never ever have a piece of code in the ISR that could potentially hog the CPU for a unpredictable amount of time. Okay, so that is the key thing here. We cannot be stuck in the ISR for an unpredictable amount of time. Okay, because you do not know when the ISR will happen, and once the ISR completes, you need to be able to go back to the main routine. Okay, so as I mentioned in the lecture slides, the ISR must do what is really important, what is critical. Okay, and the rest of it we can sort of leave it, okay, for the main routine or some other functions to carry on with the activity after that. Okay, so that is actually leading on to part B, where you ask us to look at how we can improve it. Okay, so what we can do is, after I capture the data, okay, I if the processing is quite fast, I may do it, or if not, immediately after capturing the data from the interrupt service routine, I can place it in some shared buffer. Okay, I can place it in a shared buffer, and when I come back to my main routine, okay, what I can do is, in the ISR I can set some flag. Okay, so I can copy the data to a buffer, then set some flag to be equals to 1. Okay, and when I come back here to my main routine, I can check if, for example, flag equals to equal to 1, then I go and process this data here in a normal function call. Okay, so you can see that by doing this kind of uh, activities, where I break down a big task into a few subtasks, and only the critical one I do in the ISR. The rest I do it in my main routine. Okay, so that helps me to make my ISR very compact. Okay, to just do what is critical and spend the least amount of time inside the ISR, so that I can quickly come back to the main and carry on with the rest of my activities. Okay, so that is the whole idea of question 1, to make sure we understand that in order for us to use ISRs effectively, two things. Firstly, ISRs must be kept short and very compact, okay, to do what is really important. And the second thing is, you should not have any kind of code in the ISR where you could be stuck inside the ISR for a unpredictable amount of time. Okay, that is very risky. Okay, so those are the two learning points from question 1. Okay, so for question 2, okay, semaphore and mutex. Okay, so let's just look back here. So if you recall, if let's say I have two tasks, task 1, okay, and I have task 2, okay, and if both of them have a shared critical section of the code where both of them are sort of trying to access a shared buffer, okay, so what I need to do is, before we have this critical section of the code, I must do a mutex lock, and after that I must do a mutex unlock. Same thing here, I must do a mutex lock and a mutex unlock. Okay, so that will ensure that if I'm in the middle of accessing this shared buffer and there's a context switch out, okay, I will still not be able to access this shared resource in the other task. Okay, so that is the main idea of mutex. And semaphores can also be used in a similar context, because semaphores we can create what we call a binary semaphore. That means you only have a count of 1. Okay, so in a sense I can create a binary semaphore, and I can also do the same thing. So in terms of mutex lock and unlock, I can say sempen, take the semaphore, and sempost. Okay, same thing over here, I can do a sempen and sempost. So in essence, you can say that they can be used interchangeably in this idea, but generally, okay, semaphores are used more for managing resources, okay, and another use of semaphores are to also sort of control the execution flow of multiple tasks. Okay, so if for example I have a task 1, okay, if I have a task 1 that is running, and when it's running, at some point of time I want to wait until task 2 has finished some activity. Okay, so what I can do is, when task 1 reaches that point, I can do a sempen. Okay, and when task 2 runs and completes whatever that is supposed to complete, you can do a sempost. Okay, so that will allow some form of synchronization between two tasks. Okay, so semaphores are generally used in different contexts. One is to control multiple resources, okay, that are shared by a few different tasks, or in this example here, to synchronize the flow of execution between multiple tasks. Okay, so this is the general idea of how semaphores are used, and of course you can also use them in the idea of protecting critical section of the code, but generally for that we already have a mutex. Okay, so mutex, we use them for critical section protection, and semaphores are used for resource management as well as some synchronization. Okay, let's look at the next question. In multi-threaded applications, 2 or more threads often communicate with each other by passing information through a common data structure. Okay, so if I have T1 and I have T2, okay, and both of them want to talk to each other, one common way is I can create a global variable. Okay, so that is what we already know. Okay, we have used before. So both T1 and T2 both can read and write from it. Of course, as we have seen, we need to make sure that we use mutexes to control this access. Another way of allowing two tasks to share or pass information to each other is by using what we call the task queues or message queues. Okay, so that is also what we saw. So we can create a message queue, okay, and one task can write to it, the other task can read from it. Okay, and that is also a mechanism to synchronize the behavior as well as pass data between the two tasks. Okay, so we have discussed that in quite detail in the lectures as well as in the example code that I went through. Okay, so that is for tasks to share a common data structure. In part B, we are basically giving this example where both thread A and thread B are both writing to a shared printer, and as you can see, both of them are sending data, but what the printer sort of gets is a mix of both the information coming in. Okay, so this shows a situation where there was no proper access to ensure that the printer only takes in data from one source at a time and doesn't jumble up the information that it receives. So what we need to do is, of course, we need to make sure that we use mutexes, okay, or semaphores as a ways to control the access, like what I mentioned just now. Okay, before I enter the critical section, in this case the critical section is the code that sends data to the printer. I need to make sure that when one task is sending the data to the printer, it fully completes before I let another task uh, do this similar operation. Okay, so that is what I need to do over here using both mutex and or semaphore. Okay, and do these kind of situations only happen in multi-threaded applications? Okay, not necessarily, because in a single thread application we also know that we have the concept of interrupts, okay, which means the same thing can happen. Okay, so in the main routine, if when I'm in the main routine, I'm writing to some shared buffer, okay, and if I'm interrupted here and I jump to ISR, if the ISR that is executing also tries to access this same shared buffer, then there is also a problem. Alright, okay, so we need to make sure that if there is some shared resource between the ISR and the main code in a single threaded application, then we also need to handle that very carefully. Okay, so we can also have a similar data corruption scenario in multi-threaded application as well as in single threaded applications. Okay, so the next question is on atomic operations. Okay, atomic operations are those that can execute to completion without preemption. That means once I start an operation, I will definitely complete it, okay, before I get preempted. And usually we look at it at the machine level, and or what we call the assembly language level, which you have seen in the first part of the module. Okay, so once I fetch an instruction and I pass it to the processor, it will execute, okay, to completion. And that is of course at the assembly language level. Okay, but if I look at it from the C code level, does it equate to the same thing? Okay, so this is where we have to be careful, because when I look at this instruction, it is a single instruction in C, B equals to 100. Okay, but we have to understand that most processors may not be able to support this kind of operation in a single instruction. Okay, so such an operation would require two things. Okay, so this 100 is a constant value, okay, and B is somewhere in memory. Okay, so this is in the memory. Okay, so in order for me to fulfill this instruction, what I'll need to do is I'll need to move this constant value into some register. Okay, maybe R0, R1 or whatever, and then from there I need to move it to my location in memory. So there are actually two instructions, or it's two-step process. Okay, so because it is a two-step process at the assembly language level, we say that this is non-atomic. Okay, why? Because after I complete the first instruction, there is a possibility that I can get preempted here. Okay, where before I complete the move from the register to the memory, I can get preempted. Okay, so that is why this is considered a non-atomic operation. Okay, so even though in C it is a single line, at the assembly language level it can translate to multiple lines. Okay, so it is not a atomic operation in this case. Okay, so again this shows you the importance to understand that or to sort of appreciate what we learned in the first half. Okay, where we saw that at the assembly language level, things have to be broken down at to a very simplistic step-by-step process. Okay, so that is why we need to be aware that at C or at any other higher level language, we can abstract, okay, and make it seem very simple, but at the lower level is you may still need to go through multiple steps to fulfill that requirement. Okay, so for the last question, okay, what we are going to do is we're going to look back at the code that we analyzed. Okay, I think something similar was also done in the lecture slides. Okay, so let me just go through this and see what we have. So we have two tasks, task A and task B. Okay, and we know that task A priority is higher than task B priority. Okay, and we have a ready SAM with the initial value of 1. Okay, so let's look at what happens. Okay, so I have task A and I have task B. Okay, so what is going to happen here? So first task A will run. Okay, because task A is higher priority. But the moment task A runs, what does it do? It calls time delay. So it calls a delay of 500. Okay, 500 millisecond, and then what will happen is it will go to a block state. Okay, so from here to here it will be a block state. Okay, for 500 millisecond, and since it goes to a block state, the scheduler will be invoked, and you will see that there is task B. Correct. So since there is task B in the system, task B will be selected to run. So all the while it was in the ready state. Okay, and once task A goes to a block state, you will be able to context switch. Okay, so when you context switch means what will happen is at this point of time, okay, it will be able to transition from the ready to the run state. And once it runs, what does it do? The first thing it does is it takes the semaphore over here. So it does a SAMPAN. Okay, so originally your ready SAM is initialized to 1. Once I take the semaphore, the ready SAM will become 0. Correct? Because I already taken the semaphore. Okay, then after that, what does it do? It prints out world. Okay, so it prints out world. Okay, so this is what is printed out, and after that it posts the semaphore. Okay, so it posts the semaphore. So when you post the semaphore, what happened? The ready SAM will become 1. Ready SAM will become 1, and then it calls delay for 500. Okay, it calls delay for 500, so that it will go to a block state. Okay, so as you can see, task A was also blocked, and task B is also blocked. So there will be a period of time where both of these tasks are sort of blocked. Okay, but eventually, of course, task A, since it calls the OS delay first, it will come out of the delay first, and once it comes out of delay from the block state, it will transition to ready, and after that it will go to run because there's no other task that is in the system that is higher priority. So once it goes to run, what does it do? It takes the semaphore. Okay, so here, okay, it takes SAMPAN. So when it takes SAMPAN, what happens? Your ready SAM will become 0 because you already take the semaphore. And after that, what do? I print hello. Okay, so I'm going to print hello. And once I print hello, what do? I go back to the loop over here and I delay again. Okay, so I delay for 500. Okay, and when I delay for 500, okay, again I'll go through a block state. Okay, I'll go through a block state over here, and eventually after some time what will happen over here, I'll come out of the block state. Okay, so when I come out of the block state over here, because of the OS delay, okay, then I'll go back, and what do? I try to, so over here eventually I will come out of the block state, so I'll go to ready, and then I'll go to run. Okay, so when I come to the run state, what happens is I call SAMPAN. Okay, I call SAMPAN, and at this point of time, what happens? Okay, we can see that the semaphore is 0. Correct, ready SAM value is 0. So when I try to do a SAMPAN, the ready SAM is still 0. Correct. Okay, so when the ready SAM is still 0, what happens? You cannot get the semaphore, so you will go to a block state. Okay, so you have to remember that the task A took the semaphore, okay, but it did not return it. So since it did not return it, the ready sem values remains at 0. So when this task runs and it tries to take the semaphore, it gets blocked. Okay, so when it gets blocked, okay, what happens? Okay, it cannot carry on, and eventually coming back here to task A, the OS 500 time will finish, and when I finish, I come out of the block state over here. Okay, the first thing that I do is I also try to take the semaphore. Okay, so I try to take the sem pen over here, and what happens? The ready semaphore is still 0, correct? Nobody returned it. So since nobody returned it, you will go to a block state. Okay, so you can see that task A will also be blocked indefinitely, and task B will also be blocked indefinitely, because both of them are waiting for a semaphore, okay, but nobody is releasing the semaphore. Okay, so that is basically what you would observe. So what you would observe is the printout, okay, on the screen, okay, would be world, okay, which is this, followed by hello, and that's it. You will not see any other printout, because in the subsequent iteration of the loop, both of them try to take the semaphore and both of them do not get it. Okay, so that is what you would observe. Okay, and this timing diagram or state transition diagram basically shows you what is happening. Okay, so I hope with this the idea of how semaphores work is clear, okay, in a multi-threaded context. And of course we have gone through detailed examples in the lecture slides as well, okay, and the sample code. So I hope all those is clear. Okay, so in the next tutorial we'll be looking at another topic, which is on memory and cache. Okay, so that's about it. Thank you.